Enthalpy. Enthalpy H. When heat is held constant, we have delta H, which is the enthalpy. Before we had Q as heat, and Q is heat, but when everything is done in the open air, enthalpy and heat are essentially the same thing. So Q will equal delta H. So for our purposes, Q will equal delta H, the enthalpy. And again, that is just heat when the pressure is constant. So let's look at these. Same equation, Q equals mc delta T. We have delta H equals mc delta T. Now the key here is if we have a positive delta H, we have an endothermic reaction. If we have a negative delta H, we have an exothermic, meaning it gave away heat. If it's endothermic, it absorbs heat. If more energy is put in to break bonds and is released, the reaction is endothermic. So that means if we put more energy into that system to break all those bonds than what was released, we're putting energy into it. It's endothermic. If we have a reaction and we have a lot of energy released, more than it was put into it, then the reaction is exothermic. It's giving off energy. So example, if we have this reaction of calcium oxide plus water, and in the product of calcium hydroxide, it gives off 65.2 kilojoules of heat. That's a negative enthalpy, so that's exothermic. Here we have these reactants. We have to put heat into it. We put 129 kilojoules into it in order to get the product. So if we put heat into something to get a product that's endothermic. Let's try a fun, or shall I say super fun problem. How many joules are needed to warm 500 grams of water from 15 degrees to 100 degrees Celsius? Alrighty, so we have our equation, H equals mc delta T. We want joules. Delta H will, as it is equal to Q with pressure the same, we're going to use the same constants or units for heat. So it'll be joules. M is mass, so we have 500 grams. So we're just going to plug in. C is 4.18. Delta T, 15 to 100, that is going to be 85. And we just, carry the 2. And with sig figs, we have 1.777 times 10 to the 5th joules. So that's how many are needed to heat or warm 500 grams of water from 15 to 100 degrees. So if we're trying to boil, that is about 2 cups of water. To boil it, we're going to need that many joules in order to heat that up to boiling. If we have 458 calories of energy added to 120 grams of water, so we're heating up some water, 120 grams of it, which is 120 milliliters, at 25 degrees, what will the final temperature be? So let's see. Let's write down everything we're given. Calories of energy, that's the heat. So I have delta H equals 458 calories. The mass is 120 grams. 25 degrees, what will the final temperature be? So T1 equals 25 degrees Celsius. And we're using calories, so that means our specific heat capacity can just be 1, which makes everything nice and easy. So really, we're just going to have to solve for T2. So we have delta H equals mc delta T. So that's delta H equals mc times T2 minus T1. So let's just solve for this. Delta H divided by mc equals T2 minus T1. Plug in. That's the fun part. And we will find that T2 equals 28 degrees Celsius. And that is our final answer. If we added 458 calories of energy to about 120 milliliters of water, and it's at 25 degrees. That means it will rise 3 degrees Celsius. Calorimetry is a technique that you can measure calories. Measure calories, or measure heat, with the concept that the energy changes when two substances are combined. Heat will be released by a system, and that is equal to the heat absorbed by the surroundings. So if we have some water here, and we have some reaction going on, it will release heat to the water. The system here, this is a system, it will release heat to the water, and actually I should probably draw it somewhere else. In this case, the water, as a reaction takes place, that will absorb the heat, and we'll be able to measure that heat, because from the system will release heat, the surroundings will absorb it, and vice versa. So the surroundings might release heat to the system, and we can measure the temperature change. It's a way that we can measure calories. So if we put a, let's say, a peanut, if this is the system, this peanut, and we burn it, it reacts, it will go to the surroundings, the heat will go to the surroundings of, say, water, and we can measure the heat of that, and that heat is the direct amount of heat produced by that system, and we can measure the calories. Now let's say we're going to take some metal, and we put that metal in some water. We heat that metal up, it's like a real hot coal or something, and we just put in some water. A better piece, let's say a nail. We put it in some water, and the heat, it will be released into the water. Now the enthalpy of the metal is equal to the opposite but same value of the enthalpy of the water. Because this was a system, it gives off to the surroundings of the water. Thus, therefore, it hence follows that mc delta T is equal to the opposite of mc delta T. So they're equal, but opposite signs. We need to keep that in mind. So if we're heating this piece of metal, it's going to have the exact same enthalpy with different signs in the water of the surroundings. Now let's look at a calorimetry example here. We have a hot pack with mass of 25 grams and a temperature of 95 degrees is added to a 150 gram sample of water at 25 degrees. The final temperature is 75 degrees. What is the specific heat capacity of the hot pack? Well, so let's visualize that. We put a hot pack, that is, into some water, and then this is 95 degrees. The water is 25 degrees. So the hot pack obviously will give off water heat to the water, and until we have an equilibrium of 75 degrees Celsius, both the hot pack and the water will be 75 degrees Celsius. And what is the heat capacity of that hot pack in order to accomplish that? Well, we have to set up the equation that we just looked like. The heat of the hot pack, mc delta T, equals opposite of the heat of the water, mc delta T. So it's delta H equals opposite delta H of the water. A different way to put it, of the hot pack is equal to the opposite of the water. Now what we really have to do is just plug in and solve. So we have a mass here of 25. We don't know C. What is delta T? Well, T2 we know is 75 degrees. That's the final temperature. T2 is 75 minus 95 equals opposite or negative the mass of the water. We have 150 grams times the heat capacity of the water, and we'll use, let's be easy here, let's use 1 make it in calories. Delta T, we know T final is 75. T initial of the water is 25 degrees. So we are just solving for C here, the specific heat capacity of the hot pack. So we multiply everything out, we get minus 500C equals minus 7,500, and we find that C will equal 15, specific heat will equal 15 calories per gram Celsius. So that is the specific heat of that hot pack, which is actually a pretty high specific heat. So it really holds on to that heat pretty well. That's probably why it's a hot pack. Now, before we go on, I want to just give you some heads up about, we have a lot of definitions, we have a lot of terms that might be a little confusing, and you'll hear it a bunch. So I just want to throw them out there at first, just tell you what we're going to go over, because you might get them confused. You might say, well, I thought this was this, and this was that, and this was this. But let's look at what I'm talking about here. There's a lot of heats of. We're going to talk about the heat of reaction. We're going to talk about the heat of combustion. We're going to talk about the heat of formation. We're going to talk about the heat of solution, and also the heat of fusion, solidification, vaporization, and condensation. So these are all different things. So you might want to just take note of this, because when you hear it come out at you, you'll know that they are different things. So you might want to define those, write those down. As we go through this, we will go over them, but I just want to give you that heads up.